Okay, so let's look at the ideal gas law. So the ideal gas law is PV is equal to nRT. So what exactly is P? Well, P is pressure. Okay, how do we measure pressure? Well, we measure pressure in atmosphere. So it has the unit atmosphere. So you'll usually see in questions or practice questions or exam questions that they'll tell you either 3 ATM, or they might even tell you in situations, they might tell you kPa. And how can we go from ATM to kPa? Well, we can say kPa divided by 101.35. Okay, to go from kPa to atmosphere. What about V? Well, V is volume. Okay, V is volume. How do we volume? The unit of measurement is usually L. Sometimes, however, you might be given as milliliters. So you just divide simply by 1,000. Okay, very simple. Divide by 1,000. What about N? Well, N is the number of moles. Okay, and it has the unit measurement of mole. Well, what about R? Well, R is the ideal gas constant. And the ideal gas constant is 0.0821 liters times atmosphere per, or I guess we can say times mole to the power of -1 times Kelvin, or per mole per Kelvin. Okay, then we have T. Final one is our temperature. And our temperature, we always want it in Kelvin. So quick example, how do I go from 10 degrees Celsius to Kelvin? Well, we can say to go from, let's say Celsius, I can simply say, well, the degrees Celsius, or if I want to go to T sub K, or let's say we want to go from Kelvin, all I can do is I can take my degrees Celsius and I can add 273. So in this case, let's substitute. We have 10 degrees Celsius and I want to add 273. So that gives me 283 Kelvin. Okay, let's look at 4 examples. So you fill the rigid container, metal container, with a volume of 20 liters with nitrogen gas to a pressure of 197 atmosphere at 28 degrees Celsius. How many moles of gas are present in the container? Okay, let's write down our formula. We have PV. Oh, excuse me, my point is a bit big there. Let's change the brush size to 4. PV is equal to nRT. Now, we want to calculate for N. So I can simply divide both sides by RT. So let's rewrite for N. Again, I just like to write my equations. On the left-hand side is whatever I want to solve, and on the right-hand side would be my calculations. Just think it looks very neat. So in this case, we have PV over RT. Okay, now let's list what we have. Well, in this case, they say we have our volume, right? Our volume is given to us as 20 liters. We have our pressure. Our pressure is given to us as 197 atmosphere. We have our temperature, which is 28 degrees Celsius. Well, now, as I've spoken to you before, we always want to convert our Celsius to Kelvin. So all I do is add 273. And this gives me 301 Kelvin. Well, what about the ideal gas constant? Well, the ideal gas constant, since we have atmosphere and since we have liter, it would make most sense to use the atmosphere liter. Liter times atmosphere per mole per Kelvin. And we are calculating for N. So we don't have N. Okay, so let's substitute what we have. So I can now say, well, N is equal, it's going to be a bit of a long equation. Let's put in our pressure. We have our pressure of 197 atmosphere. We have our volume. Our volume is 20 liters. we have our ideal gas constant, which is 0.0821 liter times atmosphere per Kelvin per mole. Now, in this situation, sometimes in physics or chemistry, it's written in a way where you have negative exponents. So you'd have times mole to the power of -1 times Kelvin to the power of -1. Now, if you're familiar with exponential rules, well, this just means we have to swap it to an opposite side, right? So if it's a numerator, to make it positive, it becomes a denominator, vice versa. So in this case, well, I have below the line is my moles per Kelvin, so it should look something like this per Kelvin. But now I'm going to just simply write this on my numerator, or as my numerator, to create positive exponents. Okay, per Kelvin. And then we have our temperature. Our temperature is given to us as 301 Kelvin. Now we can do a calculation. Well, my atmospheres cancel out. Let me use different colors. My atmospheres cancel out. My liters cancel out. My Kelvin cancels out. And look at that. I'm left with moles. So now we know we can solve for N. So let's find a calculator. Luckily I got one here. So 179 multiplied 20, that gives me 3,940. We're going to divide that by 0.0821 times 301. That gives me 24.7121. And then if we calculate for N, we get divided by 24.7121, which is 159 mole. Okay, so there's my final answer. Now for the next example, I'm going to make the example a lot more difficult, so we can look at even in-depth or more in-depth conversions. So let's go to example 2. Let's look at the next example. Well, how many moles of gas will a 1,250 milliliter flask hold at 35 degrees Celsius and a pressure of 95.4 kilopascals? Okay. Well, again, we know we've solved for N already. So N is equal to the pressure times the volume over the ideal gas constant times the temperature. Now, this one's a little bit tricky because now we have kPa, we have milliliters, and we have degrees Celsius. So we need to do 3 separate conversions. Or at least that's what I do, you know, just to make work easier for myself. You might differ, you know, it depends on your educator. You can also work in kPa, so in that case we'll use joules. But for now, let's look at or let's do a little bit of a long conversion. Maybe you learn something. Okay, so first things first. Well, I want to find my pressure in atmospheres. So how can I do that? Well, to find pressure in atmospheres, I'm going to take my kilopascals and I'm going to divide this with 101.35. Okay, 101.35. Now, I'll get to the calculations in a bit. I just want to look at conversions now. Well, how do I go from milliliters to liters? Oh, that's very simple. All we do is we take 155 milliliters and we want to cancel out to get liters. So how do I do that? Well, I can say 1,000 milliliters, right? Milliliters is equal to 1 liter. In this case, our milliliters cancel out. So we simply have 125 divided by 1,000. Can cancel. That gives me 1.25 liters. Okay, so now we have our V. Okay, we have our V. And let's quickly do this one actually. So we are given to 94.4 kPa. I want to divide that with 101.35. If I do this, let me grab a little calculator quick. 35 or 95.4 divided by 101.35. That gives me, okay, I'm going to round this, 0.941. Okay, so what have we found so far? So we found P. We found V. We know our ideal gas constant, right? What's our ideal gas constant again? Well, the one I'm going to use is 0.0281 liters times atmosphere per mole per Kelvin. Okay? And then what's left? Our temperature. Temperature I'm going to do in red. Well, how do we go from, if you recall, how do we go from degrees Celsius to Kelvin? Oh, that's 35, excuse me. 35 plus 273. That's going to give me 3 plus 5 is 8. 308. Okay, 308 Kelvin. Let me just double check that. 8, 3, 1 goes over 308 Kelvin. So now we can go plug in our values. Okay, we can go plug in our values. Now you can obviously if you really want to, you can do all of these conversions within the calculation. So you're gonna have one massive calculation. Okay, you can do that. Personally, for me, I don't. I wouldn't really recommend it. But again, you can obviously do what you want. I mean, as long as we find the correct moles, right? As a point. So again, we're calculating for moles. After this, I'll do one more example, maybe where we calculate the temperature or something. So let's see. So pressure. What's our pressure? Well, we found our pressure. 0.941. Okay, atmosphere. So I converted it from kilopascals to atmosphere by dividing it by 101.35. Okay, we converted our milliliters to liters, which is 1.25 milliliters, or liters, excuse me. And then we know our mole and our Kelvin will go to the top of the equation. Why is that? Because we have negative exponents, and then following exponential rules to create a positive or non-radical form, we just move it to the numerator from a denominator. Okay, or I mean, if you really want to be fancy, you can multiply both with the reciprocal, you know. But let's just do this one for now. Let's go to the next one. So now my universal gas constant, my ideal gas constant, excuse me, is going to be 0.0821 liters times atmosphere. Liters times atmosphere. And we want to multiply this with temperature in Kelvin, which was 308 K. Okay, let's do some cancellations. Let's cancel out these bad boys. Okay, atmosphere, goodbye. Liters, goodbye. Kelvin, goodbye. We left with our little moly. Little moly moles. Okay, we got them, ladies and gentlemen. We got N. So let's do this calculation now. Okay, so I'm going to say 0.941 times 1.25. That gives me, oh my goodness gracious. And you can obviously skip these calculations depending on the mark scheme, right? If the mark scheme is like 4 marks, maybe add some calculations on the side, or unit conversions, make sure your work is shown. So let me quickly multiply the numerator. So that's going to give me 308, which is 25.2868, and this is moles. So if I do this division, I get divided by 25.2686, I get 0.64 moles. 0.06. We can round this off to 65 mole. Okay, so there's my final answer. So what exactly did I do here? Well, I just did some conversions, right? I just took my kilopascals to atmospheres, and then I took my milliliters to liters, and obviously we need to take our degrees Celsius to Kelvin. And then we plug in our values, we can cancel out all our units, and we get our final answer. So maybe I'll do 2 more examples. One where we can calculate pressure, and then one where we can calculate maybe temperature. Okay, so let's look at this example. A sample of nitrogen gas occupies a volume of 10 liters at pressure 2 atmosphere. If the sample contains 0.5 moles of nitrogen gas, what is the temperature in Kelvin? So let's write our formula. Our formula is PV is equal to nRT. In this case, we're solving for T. So I can rewrite T as PV divided by nR. So let's see what we got. We have our volume. Our volume is given to us as 10 liters. We have our pressure, which is given to us as 2 atmosphere. We have our moles, so N is equal to 0.5 moles. And we have our ideal gas constant, which is 0.0821 liters times atmosphere per mole per Kelvin. Okay, so let's plug in our values. Very simple stuff. So let's calculate for T. So now we know that if we solve this equation when we plug in all our variables, excuse me, I'm not feeling too well today. If we plug in all our values, we should have all our units cancel out, and we should only be left with K, since our temperature is measured in Kelvin. So let's do this one. Okay, so pressure. Pressure is 2 atmosphere. We're going to multiply this with the 10 liters of volume. We have 0.5 mole. Let's just write MOL. And we're going to multiply this with our ideal gas constant. So our ideal gas constant is 0.0821 liters times atmosphere. And now I'm going to swap from my numerator to my denominator by changing my symbols. So let's say we're given, we have mole to the power of -1, multiply Kelvin, power of -1. I'm going to cancel these two to move them to move them to the numerator. Kelvin. Oh, I'm so sorry about that. So let's see. Moles cancel. My liters cancel. My atmosphere cancel. Oh, and I'm left with Kelvin. Look at that. So we have 20 Kelvin over, let me grab my Casio FX 991EX. Okay. So 0.5 multiply 0.0821. I get 0.04105. And then if I take 20, I divide it by 0.04105, I get 400. I get approximately, okay, approximately 487 Kelvin. Now, what if they ask you to put your final answer in Celsius? We can then say, well, to get my temperature in Celsius is going to be my temperature in Kelvin minus 273. So let's substitute what we have. We have 273 Kelvin minus, we have 487 Kelvin, excuse me, minus 273. That gives me minus 273. That gives me 214 degrees Celsius. Okay, so this would be my final answer, however, but if I'm asked to get my temperature in degrees Celsius, this is what we'll do. The process will follow. Okay, let's look at the final example. A mixture of 0.3 moles of helium and 0.2 moles of neon is kept at a temperature of 300 Kelvin in a sealed container. The total pressure exerted on the mixture is 3 atmosphere. What is the volume of the container? Okay, so I'm going to keep doing this. nRT. We're going to solve for volume. So we have nRT over P. Okay, divide both sides by P. So let's see. Our N. Now in this case, we need to find the total number of moles. So what I can do is I can say N total is going to be equal to the moles of helium. So He for helium. And I can add this to the moles of neon. So it's going to be Ne. That's going to give me 0.3 plus 0.2, and we have a total moles of 0.5 moles. Okay, that's our moles that we're going to use. As for the temperature is given as 300 Kelvin. Sorry if I sound a little bit tired. I'm a bit sick, a little bit. And let's see. We have our ideal gas constant. So by now we can sort of see that our ideal gas constant is some notable constant. So it's going to be liters times atmosphere per mole per Kelvin. Our pressure is also given to us. Our pressure is 3 atmosphere. So now we can plug these things in to solve our volume. Okay. Now if we cancel out all our units again, we should find liters. If we don't find liters, we made some mistake. So we can put the total number of moles first. The total number of moles that we calculated was 0.5 mole. We're going to multiply this with the ideal gas constant, which is 0.0821 liters times atmosphere. Now instead of going from a numerator to denominator, I'm going to simply place this over mole times Kelvin. Okay, and then we have our, let me quickly add our temperature. Our temperature is 300 K. And then we have our pressure, which is 3 atmosphere. So let's see. Our moles cancel. Our Kelvin cancel. Our atmosphere cancel. And look at that. We're left with liters, which would be a unit of measurement for volume. Okay, so I'm going to quickly do this equation. So let's say 0.5 multiply 0.0821 multiply 300. That gives me 12 point. I have no idea why I just wrote the 2 first over 3. That seems so approximately. Okay. Let's see if we can actually get an exact value over here. 0.315 over 3. That gives me, oh, I can actually, I don't need to write approximately because I can get an exact value. Okay, so it's exactly 4.105 liters. So my container consists out of, or can withhold a volume of 4.105 liters. Okay, so my advice would be to note what the ideal gas constant is. This might usually be given to you in a high school setting, I think. It also depends which program you use. So let's say you study some programs. Ideal gas laws are effective in chemistry. But let's say you study something like IB physics. The ideal gas law is relevant into the physics curriculum as well. But if you're studying, there's this American curriculum. The ideal gas law will be present in your chemistry curriculum, but not really the physics curriculum or the conceptual understanding of physics. So this is worth noting for chemistry students and physics IB students, at least. Anyway, I hope this helps. Best of luck.